We're now finishing up sort of the first major section of this unit, which is curve sketching. So here's a little summary of everything we've done so far. If you want to graph something, what are all the things that you can do? Well, you can start by using some of your skills from the past, finding your x-intercepts and your y-intercepts. If there are any asymptotes or any non-permissible values, you can put those in right away as well. So it gives you some stuff about your original graph that you've learned from the past. For the horizontal asymptotes, you can imagine when it says use the limiting process here, think about what happens when x gets really, really big. And if you had a function like this, and you were asked, what is the horizontal asymptote? Well, the limiting process says as x gets really, really big, the main thing that's going to affect this function are the x squareds. Because as x gets big, x squared gets bigger a lot faster than 3x does. So if you just think about the x squareds, and you say, well, what happens to that as x gets really, really big? If I ignore all of the other things, like I ignore the 3x, this simplifies to 1/2. And so that function would have a horizontal asymptote at y equals 1/2. The calculus stuff that we've been doing is finding your stationary points and your inflection points. You're going to do your first derivative test to find out where your function is increasing and decreasing, to find out if things are maximums or minimums. You're going to use your second derivative, not second derivative test. Remember, first derivative test and second derivative test are both for maximum and minimums. The first derivative says where things are increasing and decreasing. The second derivative says where things are concave up or concave down. So we can find our local max and local mins, or whether we have a stationary point of inflection and our other points of inflection as well. Find out where it's increasing and decreasing, concave up and concave down, and you have enough information to sketch the whole graph. So what does this look like? We'll do a couple here together. Polynomial functions. Can you find x-intercepts and y-intercepts? Y-intercept is the easiest. You plug in 0 for x, and you get 0. So we already know that we have the point 0, 0. X-intercepts, you plug in 0 for y. How do you solve this? You factor. Can take out an x, then it becomes x squared minus 4, which factors to be x plus 2, x minus 2. So we also know we have those 3 points already. No non-permissible values, no horizontal asymptotes. Now in grade 12, when you graph this, this is how far you would have got. And you would have said, I know what an x cubed graph looks like. And you would have sketched it like this. The difference between grade 12 and now is now we're going to want to find out what those points are and graph them more accurately. How do we do that? We use calculus. So we start with our first derivative. If f of x is that, then f prime of x will be 3x squared minus 4. Setting that equal to 0 and solving for x, move the 4 over, divide by 3, square root, we get plus or minus the square root of 4 over 3. So sometimes you will go to your calculator to find out what these exact values are. So square root of 4 divided by 3 is 1.15. And so if we make our sign diagram, we will have negative 1.15 on there and 1.15 on there. These are both approximations. Plug in a number less than that, in between there, and larger than that into your derivative. So if I plug in a negative number less than negative 1, like negative 2, can you see that this is going to be positive, telling us that our function is increasing? Then negative, decreasing, then positive again, increasing. And if we plug this into our original equation, so we'll have, x cubed minus 4x. We can tell that at 1.15, we get negative 3.08. And when we plug in negative 1.15, we get positive 3.08. So now we know where those maximums and minimums are. For our second derivative, I'll put our second derivative is going to equal 6x. And that equals 0 when x is equal to 0. So we know that our inflection point is at 0, and we've already figured out the coordinates of that. If you plug a value less than 0 into your second derivative, it's negative, meaning this is concave down, and this is concave up. Drawing things now, this part's going to be concave down, this part's concave up, and this is an accurate graph, an accurate sketch of this graph. Now generally, we needed to use our calculator because of the values that were present with the square root of 4 over 3 to calculate our values for x. So if you had that on a calculator part of your exam, it would be quicker just to graph it into your graphing calculator and find your maxes and mins that way. Okay? So on the calculator part of your exam, when you're graphing, you want to use all the powers that your calculator has. Yeah. I'll put the derivatives and all of the graph information up here for you. So you can pause this online. You're not going to write this down now. Don't even try. Okay. So if you want to do this on your own and then check it, then all of the stuff is here, and there's the final graph. Just have to pause the video to check that. We are going to do this one together right now, and hopefully the next one as well. Okay. Starting with x-intercepts and y-intercepts. easier to do the y-intercept first. Y-intercept is when x is 0. Can you see that when you plug in x is 0, you are going to get 1/4. So we have the point 0, 1/4. For your x-intercept, when you plug in 0 for y, the only time a fraction is equal to 0 is if the numerator is equal to 0. And in this case, that means that x would have to be negative 1/3. So we have an x-intercept and a y-intercept. I'm going to use these double green lines whenever we switch to a different idea. So we've done intercepts first. Does this graph have any asymptotes? Yes. You will have an asymptote at x equals -2, because that's a non-permissible value. So as far as that's negative 1/3, there's x equals -2. If we were having a horizontal asymptote, if you look at your function, as x gets really, really big, what does this get close to? So again, what you can imagine is x gets really, really big, the +1 and the +4 really don't matter. If you have $1 billion and you lose $1, it's not a big deal. If you only have $1 and you lose $1, then it is a big deal. And so as x gets really, really big, we say it's going to get really close to 3x over 2x. The x's cancel out, and you get 3 over 2. So as far as where that is on our graph, we now have intercepts and asymptotes. For our first derivative, solving for this, we're going to use our quotient law. So our derivative is keep the bottom the same times the derivative of the top minus keep the top the same times the derivative of the bottom divided by the bottom squared. Simplifying this, we're going to get 6x minus 6x will be 0. 12 minus 2 is 10. Is this ever equal to 0? No. So we are not going to have any maximums or minimums. We have to remember when we do our sign diagram for our first derivative, we include not only the points where it's equal to 0, we also include our non-permissible values. Our critical points are where it's equal to 0 and our non-permissible values. We had a non-permissible value at -2. What does this tell us about our graph before -2 and after -2? If you plug something into your derivative, can you see that it's always going to be positive? So our function is always increasing. And for our second derivative, probably take the time. You could use the quotient rule again, or you could take the time to move that bottom part up to a -2. If you took the derivative of this, -2 would come out in front. Subtract 1 from the exponent, and it's a chain rule, so we'd also have to multiply by the derivative of the inside function, which is 2. And so we get -40 which is -40 over 2x plus 4 cubed. Again, this is never equal to 0, but if we drew our line here, we include all of the places where it's equal to 0 and our non-permissible value. Can you see that this is always negative? So it's going to be always concave down. That makes me feel bad. No, that's because I think it should be concave up. Yes, that's right. I was thinking of the bottom as a squared. It's not always negative, right? So let's check this. If we go less than -2, knew that something felt wrong there. Just because the top is -40 doesn't make this always negative, because the bottom is cubed. So what happens if we plug in something less than -2, like -10? The top is going to be negative, the bottom is going to be negative, making this positive, making me much happier. Whew. And if we try something larger than -2, like 0, the bottom is going to be positive, the top is going to be negative. So we know that at -2, we're going to have a point of inflection. Okay, so quickly now, we've got all the data we need. What does this mean for our graph? Well, it's not a point of inflection, actually, but concavity is going to change. We've got our 2 points there. In this section, greater than -2, it has to be increasing. It has to be concave down. This is what our graph has to look like. In our section less than -2, the only way that it can be both concave up and increasing is if it's in this section. If you wanted to add a point to this section, you could plug in something like -3 into your original function. You're going to see that you get -8 over -2. And you could add a point to that. So graph B, check the answer online. Start working on D.